Hi there, this is Mrs. Rorapa and I'm back with Laytonville Physics, and we're going to talk just briefly about the speed of electricity in wires and how is it that you can send a signal down a wire very quickly so that you could have a conversation with someone on the other end if electrons in the wire are traveling so slowly. Like, what is traveling so quickly that delivers your information, because it's not the electrons, as you saw in your reading. So I'm here to try to explain that, and the first thing I'm going to do is I'm going to disconnect this circuit. So the idea is that students will know that electric fields deliver electric signals or power at close to the speed of light. I said at the speed of light. It's not quite at the speed of light, but it's very close to the speed of light. And I'm going to try to show you why that is today. Okay, so I've got a circuit here. Here's my battery with my separation of charge in the battery, and I got a wire that connects to a light and then goes through, then the current would go through the light if it was working, and then back along the wire here. But there is no current because I have not connected the circuit. Now, as soon as I complete the circuit, then I will have established the criteria for having current go through the wire. Remember, we can't have current without a complete circuit. So as soon as I do that, then I can light this bulb. But the question is, how fast will that bulb light? I mean, when I'm in the room and I turn it on, the light seems to go on like that, right? But is it really instantaneous? And if so, why? Because the electrons it takes them several hours to move through a meter of wire. So if it takes them that long, it's not going to take a few hours to light up that bulb. It's going to light up right away. So how does that happen? So what I'm going to do is, oops, I've lost my blue here, but I'm going to connect this here to the top of the battery. Boom! Okay, and when I do that, these little boxes are supposed to represent like cars in a traffic jam. So if you imagine that the wire is a complete traffic jam, and I connect it here, as soon as I connect it, cars are going to start being able to move. And this positive charge is going to start accepting negative charges from this wire as soon as I do that. And so the signal that this feels, if it depended on the movement of the electrons to allow space for more electrons, that signal would move very slowly through the wire. But that isn't how the signal travels. Instead, as soon as this wire is connected, the charge differential here makes an electric field develop around the entire wire. So as soon as this is connected, that electric field then can propagate along the whole wire. And the electric field doesn't propagate through the wire. It propagates through the empty space on either side of the wire. And an electric field traveling, propagating through empty space, it would be like I shined a flashlight here. And the light, that's an electric field, right? That's an electromagnetic wave. That light goes out at the speed of light. Okay, so here I've connected it. There's an electric field that I've generated around the wire, and whoop, that electric field goes out along the wire. Okay, so that travels at the speed of light, and it travels outside the wire. And the reason the electrons move is they're right next to the propagation of that field, and so then they begin to move along the wire. And as soon as they move, they contribute to that field, and then so that field continues to propagate out. So field moves, electrons move, the field moves, electrons move, and it continues to do that all the way around the wire. But it doesn't do that. Each electron has to move like a teensy tiny bit within the wire. The electric field travels on the outside of the wire. I hope I've made that clear. So we can do a quick calculation to find out how fast you can deliver a signal along a wire, and in fact figure out if it actually takes the amount of time that means anything to us. So if I am here and I want to send a signal, an electromagnetic signal around the entire Earth, the Earth is about 40,000 kilometers in circumference. So that's going to be 4 times 10 to the 4th kilometers. But let's make this meters. 4 times 10, I've got to add 3 here because there's 1,000 kilometers in a meter. So I'm going to have 10 to the 7th meters. Okay, so if I've got 10 to the 7th meters, the speed of light, the speed that it's going to travel is going to be 3 times 10 to the 8th meters per second. I'm going to divide the distance by the speed to get the time. So I'm going to have 4 times 10 to the 7th meters divided by 3 times 10 to the 8th meters per second. This is going to end up in the numerator, and I'm going to end up with 0.13 times, 0.13 seconds. Okay? All right. So if I'm talking to someone who is 40,000 kilometers away, there's a 1/10 of a second, a little over a 1/10 of a second in between when I talk and when they hear me. And so that's why commonly it's a little difficult to talk to someone who's really far away, because they're not hearing you till a little bit after you think they're hearing you. And we are so attuned when we communicate with others that it makes a difference. And we're not always as able to communicate with people. If we were talking to someone who was on another planet, let's say you had a spaceship around the sun, it would take 8 seconds for your information to get, for the electric field to get from the sun. So when we talk through wires, the information travels at close to the speed of light, but even so, it still takes a little bit of time, whereas the electrons travel exceedingly slowly through the wire. Now, as soon as you set up the field, the electrons can start to move. As soon as they start to move, they can light the light. So that signal that lights the light gets there at close to the speed of light, but it doesn't travel through the wire. It travels along the outside of the wire. But the power that drives the light, that does have to travel through the wire in order to heat it. So, but it doesn't, those electrons don't have to travel very far to do that. They have to move barely at all, and they begin to heat this wire. So I hope that's made it clear. The power that drives machines has to move through the wire. That's the electrons actually moving. But the signal that travels along the wire moves at the speed of light outside the wire. Okay, thank you.